All right. So sorry, I was a little bit late today. So we want to continue to talk about coherency, and today we want to talk about consistency. Remember we said that the coherence problem is because we have a shared data, right? And we want to have our private caches for performance purposes. So what will happen is if somebody tries to, just put something into one of these caches and then tries to update this with the new value, this other cache will not see that because this is a private cache, and there will be, coherency problem, right? The solution for that we talked about, and we said that snooping is one of the key solutions for this, right? And we talked about a bunch of different, coherency protocols and so on and so forth. Essentially, we said that what will happen is you need to come up with some kind of set of rules that say, okay, if there is a cache miss, what should I do? Who should I tell? If I see someone is having a cache miss or is trying to read something or trying to write something, what else needs to be done, so on and so forth, right? We talked about a bunch of this different states and techniques. The last thing that we talked about was MOESI, right? So M for the modified, O for the owner, E for the exclusive, S for the shared, and I for the invalid. And we said that essentially each of these, we should start with an MSI shared state, which was essentially the M was when we are trying to write something to the cache, to the main memory, so everybody else has to be invalidated. Shared was for the scenario of which that data is just a clean copy of the data was shared among different cores. And I was when you don't have that copy of data because someone else wanted to write that. And so that the MSI is basically the bare minimum that we need. You technically can also use MI, but MI is just way too inefficient because there are lots of cases that you just want to read things and not write to it. So that would create lots of challenges. Then we start adding two things, O and E. The E one was for the cases that you are the only one who has that data. You really don't want to kind of pollute the cache snooping infrastructure by just keep telling that, oh, I have this data, but I want to write to it. So you become the exclusive user of that cache, and then you would just keep using it, right? And we said that essentially this is very common because for many cache lines, we don't really need to share it with anybody else. So E is actually quite helpful. The O one was for the case where someone was in M and had the data, and then someone else wants to read it. The O state is basically, if you have two cores and this one has data, without O, this one has to go through the main memory and bring this data back. And before doing that, this one has to be written back, and then this data has to be read, right? So there was two writes to the main memory and two round trips basically for main memory, which is kind of slow. So instead, what we can do is basically if we have two data and this one has the dirty copy, instead of writing it to the memory, this one can just forward it to the other cache. And we said that essentially in order to know which one has to forward to which, we need an O state who becomes the owner of that one. Okay? Any question about coherency so far? All right. So the last state that I want to add is what we call an F state or forwarder. And the reason that we want to have an F is if there are a bunch of different cores in the shared states in the S state, and a new core wants to read, the question becomes that who should provide this data, right? Should that core goes into the main memory and bring that data? Or given that every other core has this information, maybe they can forward it to that core. And then if we go with the second option, which is obviously the more efficient option, the question becomes which one of these cores. So let's say, for example, we have core number 1, core number 2, and core number 3. These two are already in S, and this one is in I, but this one wants to, switch from I to S. So between these two cores, which one should provide this data, right? One thing we can do like round robin and say, okay, whichever answer it faster, that would be easier. But that means that there will be again pollution in our snooping protocol. So what we can do is that we can define a forwarder state and say that the forwarder is the one that is responsible to forwarding the request, the clean copy. So the forwarding becomes the clean counterpart of the O, because O was providing data when the data was dirty. F becomes the one that's when the data is clean, it will provide it for us. So how do we have F? Basically, F is the old E, okay? So what we can do is saying that, okay, at some initial state, everybody is at I, right? Then there will be one core that for the first time wants to read this data. And remember, if you had E, that core transitioned from I to E in order to read that data. But then if another core wants to read it, what we had before was we had E, and we said that E has to transition from E to S, right? So what we're saying now is that if we're adding this F state, the E1 then now can transition to F, and everybody else goes to S. In that case, then the next time that somebody wants to get the data, the F will be the one that's provide the data, and the F is basically the core that was originally read this data, right? So the first core that reads this becomes the forwarder in this case, okay? So combining this all together, we will have MOESIF, 6 different coherency states. There is no further additional states rather than just 6 commonly used in most systems. Not every modern system has all these 6 different states. Some of them is MOESI, some of them is MESI. Typically, most of them have the E because E is kind of like the most useful case. But the F and the O is really depends on how much sharing is required between the users. So both O and F is kind of typically doing the same thing. It's just for the clean copy and for the dirty copy. For F, you typically need the E. It doesn't make sense to have F without E. So usually we have I, E, and F as one transition. We have I, M, and O as another transition, right? So you start from invalid or S, and you go to the M, and then you go to the O. Or we typically have I, E, and then the M, and then maybe O, right? So, and then this one is the difference between this one compared to the others is that this one is a silent transition from E to M. Okay, so it's typical that you see all of these in modern systems. You actually can't search, for example, for this given technology of Intel or AMD, which one of these are being used. Not all of them use all the 6 together. Okay, questions? Okay, so we're going to release a homework for cache coherency, and then things that we're going to discuss today on consistency as well. So you see, a bunch of different examples of this that we're going different cores, and you have to kind of keep track of different lines. So hopefully you get more, familiar with this concept once you do that test, once you do that example. Okay. We're good with coherency states. Any final question? All right. So to summarize, basically what we did was we are trying to add the states in order to do multiple, improvement in our performance. We kind of eliminate the unnecessary broadcast through, for example, having an exclusive to M state. We kind of eliminate some of the additional write-backs that we really don't need to do. We introduce cache-to-cache transfer with forwarding and owner. So we do these things in order to kind of improve our performance in all these cases. Of course, the trade-off is as you add more of these states, keeping track of more states become more complicated. But on the other hand, you get lots of performance benefits out of this. All right. The 2 final things that I want to talk about coherency before we move on to consistency issue is one of them is what we call false sharing. So a false sharing is when, I mean, as you remember, we said that the cache line have multiple blocks, right? The reason that we have multiple blocks within a cache line was we want to use locality, right? So for example, address 110, 110 and 111 and so on and so forth. Let's say if you have, 8 of these blocks, so all the way to 117, for example, all goes into one line of the cache, right? So if you want to read this, we're going to bring this. If we want to evict this, then we're going to also evict all of these things, right? So that's the idea of having a cache line. What will happen is that because of the cache coherence, we're going to have what we call a false sharing. So cache coherence also happens at the line level. So we don't do block level cache coherence. We do line level cache coherence. So if a line is shared, it means that the entire line is shared, not individual blocks. And if, for example, we want to transition from S to I, what will happen is that it means that that line of cache has to be evicted from that block, right? So it has to be evicted from that cache. So for example, if it's an L1 or L2, and we say we see that this has to transition from S to I, what it means is that we have to evict that from your cache. And when you evict that, you not only just evict that specific block, but you evict everything within that cache line. So for example, let's say 111 is the actual shared block among the cores, but when you're actually evicting it, you're going to evict everything in that line altogether, okay? And we usually call this false sharing because, for example, if 110 is not at all shared between the cores, but 111 is actually shared, if this one is shared, but this one is not, what will happen is that because this one is shared and we need to evict this, we will also evict this. And the next time that we want to read 110, the data is not going to be there. So there will be a miss. And this miss, we call it a coherence miss. Because if there weren't any coherency protocol, 110 would have been there, right? And 110 has nothing to do with the fact that we are sharing 111. They just happen to be on the same cache line. And since we keep track of cache lines, coherency states at the line level, even if this particular block or blocks are not even shared, they're gonna have to suffer from the fact that one of those blocks in that line is shared. So if you evict that and next time you want to read that it's not there, that's going to be a miss, and that would be what we call a coherence miss. So that will be added to your compulsory miss, your capacity miss, and your conflict miss. So the fourth C is what we call a coherency miss. All right. And the reason that we call it false sharing is that, yes, if you had 111 and 111 is evicted, still this is a miss, but this miss is not, it's because that you are actually sharing. But this 110 is not even shared between the caches, but you still will suffer a miss. And because of that, we call this a false sharing issue. Because 111 is shared, but 110 is not shared. And this miss is happening because you are sharing something else, but you're suffering something. You're dealing with some other block. Okay, so false sharing is basically kind of this concept that you're not really sharing that block, but since the neighboring blocks are shared, that block will also suffer and experience the same issues that the shared block will have. Does that make sense? So that's one thing I want to talk about. The second thing I want to talk about before we move on is, so we said that the solution for cache coherency is snooping, right? It's widely used in many systems, but snooping is not the only option for fixing the cache coherence problem. In fact, snooping is not great for scalability. If you have many different cores, let's say you have 64 different cores, if all of them needs to broadcast and everybody else has to kind of like, look at that bus and try to do something about it, it's not the best way to do it. So scalability is an issue for snooping-based caches. So what we can do instead is what we call a directory-based cache coherence protocol. We still do have all those states of M and S and I and so on and so forth. But instead of saying that, okay, every cache, just look at what's been broadcast and take this information, snoop the cache and make a decision. What we can do is saying that, okay, we're going to have one unified table that basically for each level, we're going to say that, okay, this is a table. And in this table, we're going to say each line. And then we're going to have multiple different entries. So for example, we're going to say where this line is stored, whether it's stored in P1 or P2 or P3 or all of them and so on and so forth. So basically, we kind of keep track of where this is. And then we're also going to keep track of the states for each one. So for example, say P1 is in I, P2 is in S, P3 is in S, maybe P4 is in I as well, okay? So for every line in the cache, in the lower level, we can have that for the higher levels. And this way, what we can do is then we don't need to, broadcast anything. If something happens, all we need to do is basically just update this for ourselves, and then send the corresponding command to those cores. So for example, if we decide that's like, P1 wants to go to the M, we tell P1 that you go to the M, and tell everybody else that you guys go to the I. So we send just a command. So basically, this is a unified table. It's a directory that everything is in that directory. And then whatever happens based off this activities goes directly into this directory. The directory decides what's the next step for every single cache, every single core. We'll send out the commands to each core and say, okay, you do this, you do that. If you don't need to do anything, then of course we don't need to send anything to those caches. And this way, this is very, very good for scalability, because all we need to do if we're adding more caches or more cores is basically adding more and more of these columns. So, and since this is just a one-time directory column, that's all we really need. And the number of broadcasts and so on stays the same, because just every directory needs to send one command to one of these cores each time. Okay? So still you're going to have all these M or S or I or E and so on. We actually may not need some of them no more, because, for example, you don't need forwarder in some cases because everything is in the directory. But generally, the assumptions are kind of similar. The only difference is that you don't need to broadcast, and you don't need to look for the broadcast, and you don't need to update that based on that broadcast. Okay? The difference, though, is that you need this directory somewhere. So that would be an additional overhead. And this directory then becomes also your bottleneck, because all the requests goes into this directory, and everything has to be done by this directory, versus on the snooping-based scenario, things were distributed. So every core was doing its own thing without really caring about the other parts of the cache, right? Or other part of the system in general. Okay? So I'm not going to go through the details of the directory, but just keep in mind that the directory is the alternative way of looking at this instead of snooping. Instead of everybody's kind of being involved, we're going to have a centralized controller unit kind of thing and say, okay, we go there, figure out things, and then just tell everybody what to do. Okay? So that's it with the coherency problem. Any final question? Yeah. So the question is for the directory base, is it one centralized table for all the cores, or it's not like we need a copy of each core? So basically, what we do is that we have a line in. So what we assume is that every line in this current cache level will be, some of these will be in the higher level, right? So we have a table for all the lines of the upper level. But we don't need to replicate these lines for every single cache. We have columns. So we have one row of the address, and then we have columns for every single core. So we're going to say, oh, this line is shared between P1 and P2. This line is not shared at all. This line maybe is in M state for P3, but in I state for everybody else. So we basically say, okay, these are all the possible addresses. For everyone, we have an entry in this table. Any other questions? All right, so now let's talk about consistency. So what is the consistency problem? The consistency problem is basically twofold. What is happening with the consistency is that if we have a multi-threaded program, multi-core program, and if we are looking at different addresses, so we're no longer talking about the same addresses, we're talking about different addresses. What will happen is that the ordering of activities within one core, or the ordering of, like, whether we are running this first or whether we are running this. So the timing between the cores will result in different values for what we assume when we are writing the program. So to give you a more concrete answer, let's, example, let's look at this. Let's look at this example. Let's say MZ and MY are two different addresses. They're initially, equal to 0. So that's 0 is stored in those two lines. And let's say we have two cores. These are part of the same program. Okay. Core number 1 is loading Z and then storing 100 to Y. Just don't, I'm not using the correct syntax for RISC-V, so just ignore that. So what this means is that I'm writing 100 to Y and I'm reading Z to X1, and core number 2 will be loading Y to X2 and then trying to write 200 to Z. Okay, and then again, Z and Y are two different addresses. So assuming that these two values are 0, can you tell me what would be the final value of X1 and X2 in this case? Any suggestion? What can be potentially the final value? Anyone? Yeah. They both be 0. How? Okay, so this is 1. Then what? Then this 2, right? And then maybe this 3, and then this 4, right? So 0, 0. Anything else? Would be the core 1 lower than the core 1 slower, and then you do the core 2. Yeah. So you do 1. So you do 1, 2, 3, 4, right? Any other suggestion? So you get 200 and 0. Okay. How? Sure. So scenario number 4 would be X100 and X2 200. And how does this work? Say it again. So this one would be first, this one would be second, maybe this one third, and this one fourth, right? Does the fourth one is possible? Is it possible? Why not? Is it? These are two different addresses though, right? Remember we had store buffers, right? So, I mean, in this core, right? If I reorder things, if I just care about this core, if I reorder this, does anything changes for core number 2? I mean, assuming that everything else is just has nothing to do with these two lines. From core 2 perspective, that doesn't happen, right? So what would happen is that, to summarize what we are saying, is that depending on how you order these instructions, both internally and externally. By internally, I mean within the core number 1 or within core number 2, and also how you interleave these instructions between each other, you might have actually various different outputs, right? So you might run this first, and then this is this next. You might run this first, and then maybe this one, and then this one, and then this one. So there could be many different interleaving. And in this interleaving scenarios, you might get different answers, right? This last one that, within one core, we might run this one first and this one next. If the program order right now is this, it might not happen because we have the reorder buffer. But if, for example, the hardware decides to move things around on the fly, then this is also a possibility. And then, in fact, in out of order execution, the compiler or the hardware may decide to do that in order to improve the performance. All right? So it's really, really hard for a programmer perspective to understand actually, if I want to use X1 after this sequence of code, what exactly X1? If I run it one time, X1 might be 0. The other times, the X1 might be 200, right? So it's going to be really weird to kind of figure out what would be the value of X1, okay? And this is what we call a memory consistency problem. So you might ask, oh, but didn't we solve this with raw data hazards? No, we didn't solve this with the raw data hazard because remember, this is not a raw data hazard. These are two separate addresses, nothing to do with each other. What we solved in raw data hazard was basically writes into the same address or writes into the same register. By the way, we didn't fix the writes into the same address. We kind of did something we called memory disambiguation, which is not important. But remember that we basically do the raw for the same address. What we are talking about here is writing to a different address. So nothing to do with raw data hazard. This is not a correctness issue either because of the fact that this is completely valid and legal transitions of instructions. Just cores can be one core might be faster, one core might be slower, so on and so forth. And basically, the reason that we had kind of like the last one was because of these load store queues, that we basically say that within each core, we are fine because even if the store happens before the load, this load store queue kind of take care of that. But once we are stepping out of the core and look at the other core, since this is not visible to the other cores, then there could be multiple different scenarios. All right. So, and then not only that, compiler, when it actually tries to write the binary, they might decide to reorder things, and that could create lots of headaches for us. Okay. So the consistency problem, basically, if I want to give you a more concrete definition, is kind of like in a twofold problem. The first one is stores and loads within the same core to different addresses might be reordered because of the compiler or the hardware optimization. And that what would happen here is that within that core, nothing bad happens. But that will mess up other cores. The assumptions about the other cores and the program within those other cores is going to be completely messed up. All right, that's number one. The second problem that we need to solve in consistency is that the timing between the cores might be different. So these two are completely independent from each other. So if I have, sequence of instructions here for core number 1, and if I have different sequence of instruction here, the timing of these two could be any overlap. So it could be something like this, it could be something like this, or it could be any overlap between these two. So we don't know, we are talking about two separate cores, each one is just running independently without checking what's going on with the other core. And we don't have any kind of like, method to kind of say that, oh, I'm here, where are you, and so on and so forth. So it's basically, we are talking about two independent things running together. So we don't have any way of knowing which one is where. And if you're assuming that, this should happen before that, we need to come up with solutions to kind of enforce that. Otherwise, in the normal system, there's no way that you tell the core number 2 that, oh, my data is here, you should be here too. Okay? Only within each core you have your PC and you kind of enforce the program order and so on and so forth. Between the cores, PCs are independent. You have no control over where your PC is for each core. Does that make sense? And consistency problem is different than coherency problem. Remember, coherency problem was for the same address, okay? So when we had the same address and it was in different private caches and tried to update the same address, we had the coherency problem. Consistency problem are talking about different addresses, okay? The fact that the timings are messed up and the reordering can mess things up even more, we will have consistency problems because the value that we assume that we're going to get, it really depends on the timing. For the coherency was writing to the same address and reading from the same address, and that could be also messed up because we have private caches. Okay, so these are two different things, kind of relevant, both caused by the fact that we have multi-threaded programs, but two separate problems, right? Okay, so let's see how to fix the consistency problem, because this is obviously needs to be fixed in order for us to be able to use this. So as I said, two separate problems. The number one problem is the timing problem, that you have two separate cores and they don't have any way of kind of like, knowing where they are. And this is not the hardware problem. This is just the way that you are writing your code. If there is what we call a race condition, that if this happens first and this happens next, versus if this happens first and this happens next is different, you get different values, you are writing a program that has race conditions. So it's on you as a programmer to kind of either eliminate these conditions, or we need to provide some primitives that we're going to talk about later in the lecture to kind of fix this. We will talk about what we call synchronization. We talk about what we call barriers, and we talk about what we call lock and release and lock in order to kind of fix this timing issue. So we basically, the idea would be that, oh, we either tell this processor that the other core is here, wait until I reach, and then we can move together. So this is more of the idea of what we call a barrier. The other one is kind of like the idea of what we call a lock, which we say that there should be an exclusiveness between the timing of things. We will talk about that as well. But let's talk about the reordering problem first. The reordering problem is saying that if I move things within one core, and it's perfectly valid and perfectly legal to do that for performance purposes, that will create lots of problems for the other core. And remember, this is basically the hardware problem, because hardware wants to get more performance and doing these kind of weird things, and the programmer has no idea that this is happening, right? So you write your program thinking that, okay, things happens in order, but in reality, things might not happen in reorder. And remember, this is very similar to the things that we did for raw data hazards, and the same thing that we did for out of order execution. Again, there we said that, we're as a programmer, we're assuming things happening in order. Hardware does things differently, and that's why we're getting this sort of problem. So we need to fix this one first. For the second one, it's on the programmer to either fix it, or we can provide some tools in the hardware for the programmer, but still the programmer needs to use those tools. So I'll talk about that as well. All right? Any questions so far? All right. So in order to fix the reordering problem, we need to know what are the possibilities. Like, is it possible to reorder these two instructions within one core or not? Is it All the loads and stores can be reordered. Only loads can be maybe reordered. Maybe only stores can be reordered. Which one is the case? And this is what we call memory model. So the memory model in programming view means that if you're writing a program for each core, you need to know what are the possibilities within that core in order to get the reordering. So for example, someone says that, x86 use what we call a total store order memory model. Other in systems such as ARM has what we call a weak consistency model. So we need to, or weak memory model. So we need to define what are these memory models, what are the different options, and once we know that, then we can as a programmer, then we can write our programs. All right. So the first thing that's typically being used, and it's what's called a very strong memory model or consistency model, is what we call sequential consistency, or SC. Okay, so this is basically what we expect. Okay, and what you guys expected as well. That if we have loads and stores within one program, the processor will see that loads and stores with the same ordering that we wrote them. Right? So if you have a load in core number 1, load and then store, sequential consistency says that if the memory model for this core is this, it is guaranteed that this happens first and this happens next. We will not have a scenario that store happens before load. So that 0, 0 or 200, 100 scenario that we talked about will be eliminated. And not only that, sequential consistency is actually pretty strong. It will also say that other processors will see the loads and stores in the same ordering. And remember, we are not just talking about only loads or only stores. We're talking about both loads and both stores. All right. So you cannot reorder stores. You cannot reorder loads. You cannot reorder loads versus stores, and you cannot do the other way. So all the 4 combinations are not allowed in sequential consistency. All right. And this is the simplest scenario, right? It basically says that, okay, whatever I write in each program, in each core, that's what's going to happen. That's what everybody else is going to see. All right. And then make your assumptions based on that. Write your program such that that's the last thing that we discussed, that things can reorder within the core, is not there. You just need to synchronize your cores and you're done. Okay. So, and this is basically says that this SC give you the same idea as an in-order processor. Everything happens in order and you're happy, right? The problem with this is that it's too slow, because it means that stores has to wait for the loads has to wait for the stores, even though they're completely separate and independent from each other. So all those, kind of, let's have a store buffer and let's write things to it and just move on and don't stall a processor and all those things, they're all going to go to the trash. It's not going to be usable with sequential consistency. Still, remember, we're talking about one core. Okay, so sequential consistency is very strong, really good, really helpful for us to kind of like fix the issues that we are worried about. But unfortunately, it's slow because it just doesn't allow you to reorder things. What you want to be able to do is some reordering, right? So the reordering can these only 4 different options, 4 different possibilities, right? So you can, you have a read after write, you have a read after read, you have a write after read, and you have a write after write, right? So these are the ordering that is possible. And when we are talking about reordering, means that we might want to, move this before this or move this before this. And remember, these are separate addresses, okay? So this is not write after write data hazard. This is write to address X and write to address Y. And what we are saying is that why won't we be able to do write to Y before write to Z? Because that doesn't change anything for us, right? But for consistency problems, that might create issues for us, right? So sequential consistency basically says that don't do any of these. Don't reorder things at all. You're not allowed to. And this fixes the issue of reordering within one core. Okay? Any questions? Okay. But what we really want to do is that for performance purposes within one core, we want to be able to move things. Especially what we really want to do is we want for the stores to happen before loads or loads happens before stores. Because these are, again, separate addresses. So why should I wait for the stores to finish when I want to read completely different things from my memory? So some reordering would be nice, right? So in order to fix this, we are using what we call a relaxed or weaker model memory models. What weaker means that assuming that sequential consistency is the strongest consistency model that we can have, anything that's kind of relaxed one or multiple of these assumptions becomes what we call a weak consistency model. And this is good because we want this to get performance, and some of them are actually unnecessary. Maybe we can fix this. All right. So what we will get is we're gonna relax some of this, and the one that is very commonly used is what's called a TSO model or total store model. Okay, so the total store model is slightly different than sequential consistency. What it says is that within each core, it's safe to read address B before think there's like a power outage or something, right? All right, so there was a power outage, so we're back. Okay, so the TSO model says that if we have address B or address X or Y, we can read address B before the write to address A is seen by all the other processors. So basically what it means is that you can reorder reads before writes, okay? And when we are saying reorder reads before writes, again, I want to emphasize that we are talking about different addresses, okay? We don't say that reads before writes of the same address. That would be a correctness issue, and we talked about that extensively in the class, that those things will be solved with out-of-order execution anyway. We're talking about separate addresses, has nothing to do with each other. You can actually move things above. And the way that we're going to do this, if you remember load store queues, we're going to have that, right? So when we have a store, if you remember what we were doing is that we had a queue. We put the store into the queue and then move on. We actually don't issue the store to the cache hierarchy. We just put it into our internal buffer. And then if we have a load here, then we go to the load and see this is there, and we're going to read that value, right? Remember, from the memory perspective and from the other core's perspective, we never see the store happening, but we see the store is happening, right? So that's why kind of store happens before load internally. Externally, what will happen is that the other cores may not see that there is an update in this value for our core. Okay, so what it says is that if you have load store queues internally within each core, you can reorder loads before stores because there's no problem as long as you have the stores. You have the store buffer. Okay. And this is what we call a total store order or TSO model. Remember that this doesn't fix the issue of other cores. Still, other cores won't see that we are writing things and so on. But internally, within each core, we can freely move loads after or before stores. Okay? So let's see how TSO can help us. So TSO, if you have a scenario like this, that let's say A is equal to 0, and flag is also equal to 0, what the TSO will give us is that since we have the store buffer, we're going to see that this store is actually happening in order from the other cores. Okay, so if it didn't have TSO and we didn't have any consistency models, since these two could have been reordered, this might have been happened first and this might be happened second. So this one first and this one second. And if you look at the code at 2, it basically says that wait until the flag becomes 1 and then read A. So what this code on the right side says is that I'm going to just wait until the flag is 1 and then I'm going to read A. And our assumption is probably is that, if my code is like this, given that A happens before flag, this one should be guaranteed that it's going to read 1, right? If we don't have any consistency model, if we are not using sequential and or TSO model, A might actually read 0, right? Why? Because if these two are reordered, and we said that it's totally possible that we reorder those, we're going to get that problem. But what TSO and sequential consistency will give us is that you can reorder load before writes, but you cannot reorder anything else. You cannot reorder writes and writes. So what this says is that under TSO, this will happen first, and this will happen second. And as a result, these other cores will see that the flags becomes equal to 1 first. And once we are inside this loops, it's guaranteed that A is already equal to 1. Same for sequential consistency, because remember, for sequential consistency, we said that everything has to happen in order. And for TSO, we are just saying that let's relax the loads after stores, and let's not do that. But everything else has to remain the same, which means that I cannot reorder writes after writes. Okay? So that's how TSO can help us, how sequential consistency can help us as another thing as well. But TSO is slightly better because then we are also getting a little bit more performance out of this. Any questions? You good? Okay. So going back to the original example that I gave you, under TSO and sequential consistency, can you tell me which one of those 4s are kind of going to be eliminated? Any suggestion? So remember, we had x1 equal to 0 and x2 equal to 0. We had x1 equal to 200 and x2 equal to 0. We had the other way around. And we had scenario which that this one was 100 and this one was 200. So tell me, which one of these is not possible under sequential consistency? Any suggestion? The first one, why? We are guaranteed to, so what sequential consistency gives you is load should happen before stores in each core, right? So what sequential consistency will eliminate that this cannot happen before this, and this cannot happen before this, all right? So what we will guarantee, but again, remember that the timing issue is not fixed by either sequential consistency or TSO. So this might happen first, then maybe this one, and then this one, and then this one. Sorry, 2, 3, and 4. It's not possible to happen is that this one happens first, and after sometimes this one happens. This is not possible. Okay? So in that case, you will see that a scenario like this is not possible, right? Because you cannot run this first and run this first before any of these two. You can run this first before this one. That's totally fine. But you cannot run this before this, and you cannot run this before this. So the last one is going to be eliminated by sequential consistency, because you cannot do stores before load. You cannot do loads before stores even, all right? But what about TSO? Does TSO allow this or no? Remember, the TSO was basically saying that I cannot reorder stores I cannot reorder loads. What is actually can be done is I can move loads after stores or stores after loads. That's totally valid in TSO. So what does this mean is that in under TSO, still we're gonna get this scenario here, okay? Because still store might happen before load in core number 1, and in core number 2 stores also can happen before load. All right. So TSO allows two things to be reordered within one core, and because of that, we're gonna still have the same problem that we had in before. Sequential consistency does not allow it. But what the TSO will give you is scenarios like this, that if you write right, then you cannot reorder writes. Okay? So just don't confuse and don't mix these two together. TSO will give you a consistent behavior among the writes on the other side for other cores. Sequential consistency gives you everything, so nothing can be reordered. And as a result, you might have some of these scenarios, and you may not have the other scenarios. Is that clear? Good? All right. So to just summarize what we said so far is TSO and sequential consistency try to give you kind of like list of available options. Sequential consistency is very, very strict. It basically says no reordering at all. TSO is basically saying that you can reorder loads and stores. It's just from the other core's points of view, writes should happen in order. And this will boost the performance per core because then you don't need to wait for the stores. But still, we're going to have the timing problem that we had before, even with TSO. So TSO does not solve all the problems. Okay? There's also other consistency models, the weaker consistency models. Each one has different assumptions and what is visible and what is not visible. The difference between them is just getting performance, because obviously you want to be able within each core to do any reordering as much as you want, and that gives you the maximum performance. But that also means that the programmer model would be very, very complex. So it's a trade-off between the performance you're going to get versus the complexity. And typically, different microarchitectures and different companies use different models. So Intel x86 is using TSO, but ARM, for example, using a weaker consistency model. All right. I'll talk about one more consistency model in next few slides. But before that, I want to talk about the timing issue and how we actually synchronize these cores together. Any questions? All right. So now that we know this, let's actually see that, okay, at the programmer side, what needs to be done and how we can help the programmer to kind of like, fix this issue. First of all, the programmer needs to know what is the memory model. Okay, so the programmer needs to know that what is the underlying hardware and what is the memory model of that underlying hardware. Once it knows that, then the programmer can do one thing and say that, okay, I'm not going to write race condition in my program, which means that I'm not going to have a scenario at which that if this happens before this versus if things happens in order, I'm going to get different results. It's going to be very, very hard, but it's doable to write programs like that. Okay, so we typically call them race-free program. All right. The other option is let the hardware kind of keep track of things. And if it sees that there is an issue, kind of recover. So it's basically more of like a speculation. We need to add lots of things to the hardware. And that way we might be able to fix this. This is not also a very popular scenario because of the many things that we need to add to hardware to fix this. But just keep in mind that that could be also a solution. The real solution that widely used is the notion of synchronization. All right. So the synchronization basically says that the programmer, with help of some primitives that the hardware will provide, and we're going to talk about in the next few slides, going to use this APIs or this primitives in order to kind of like, fix the ordering and fix the timing among the cores. So basically say, okay, let's all wait until this point and then move forward afterwards. So you still might have race conditions, but using the synchronization methods, you kind of like say, okay, let's use those. So it's a similar things that we use also in our everyday lives, right? So you with your friends goes to some place, you want to reach to the same place at the same time. One thing you can do is that, be in the lock steps, and every step you can do the same. Instead, what you can do is saying that, okay, I want to go from point A to B. So let's, for example, say that let's meet at C until like 1:30 or whatever. Once you reach the C, you say, okay, let's go separately. Again, we're gonna meet each other at B, and so on and so forth. So there will be points that's kind of like gonna synchronize, check with each other, and move forward and move forward. All right. So there are two major ways of synchronization. The first model is what we call a producer-consumer. There will be a scenario which like one is going to use something, produce something, the other one going to consume and take that and move it forward, and then we can do it back and forth. The other one is what we call a mutual exclusiveness, and that's the one that's more popular. And it's basically say that if we have a shared resource, what we can do is that we always guarantee that only one of them is using this. If we do that, then basically we don't have race conditions, because only one of them is active and changing things in that shared resource. All right. So what are the options, and what are the solutions, and what are the hardware primitives for synchronization? There are three different things that we need to discuss. The first one is what we call fences. All right. So think about fence as an actual instruction, same as your add or XOR or multiply and so on. What fence does is basically literally a fence. It says that everything before fence has to happen before everything after fence. So if I have a sequence of instructions and I have a fence, which is basically literally an instruction, and I have a bunch of different instructions, it basically says that I don't care what are you doing here. You have load stores, you want to move things around, do it. When it reaches to the fence, all these things should be finished. And you cannot move things from this side of fence to the other side of fence, or vice versa. Okay? So this is basically say that everything happens after this fence instructions should happen after all the instructions before this fence. It's literally a fence. So things on those two separate sides are separate from each other. Okay? So for example, if I have a load and store, in normal condition, we said that we can reorder these things if you want to. If I add a fence here, then I can no longer do the store before load, because the fence literally says that we are not allowed to move things after the fence to the before the fence, or the other way around. Okay? So if you add these fences to your program, then you within each core, you can kind of enforce what level of reordering can happen. So you can say that, okay, for this part of my program, I don't care about reordering, but maybe for this part of the program, I do care about my reordering. So I'm going to put fences here and there. And the interesting thing about fences is typically, especially for RISC-V, we have like, R fence and L fence. So we have for loads, we have fence. We have for writes, we have fence. And then we have a fence for both of them. So what it means is that if we have an L fence, it means that loads cannot be reordered, but we are safe to reorder stores before loads. So we don't care about stores. We only care about loads, and loads should happen in order. The write fence means that writes should happen in order, and we don't care about loads. So you can just reorder loads before and after fence. And the load write one is basically says that either load or stores have to happen using fence. So you cannot reorder any of those before or after fence. Does that make sense? So fences kind of like fix this issue within the course. Whenever you are in doubt of what can I do in order to, avoid reordering within my core, just use fences whenever it's necessary. Just add them at the binary level or at the program level, and you're good. About between the cores, fences wouldn't help. What will help is what we call a semaphore, or in other words, barriers. Okay, so the barriers is basically this notion of synchronization of multiple cores together. Okay, typically implemented in software or the operating system. So what it does is basically think about it literally as lines that we add, and basically say that we cannot go beyond this point until this other application reaches to this point. So for example, let's say that this core is here and starts running these instructions. Since this barrier is actually, this instruction is on the top side of the barriers and this instruction is the bottom side of this barrier, I cannot execute this before I reach to this point. Okay, so these are the same barriers. So I need to run this first. Then I need to run this, or maybe there is some reordering, I don't know. So whatever happens here, I don't know. But what I do know is that when I reach to this point, it is guaranteed that this part has not been started yet, because this is at the bottom side of my barrier. Okay, so barrier is the synchronization points that says anything before the barrier has to happen for all the cores. Then anything after the barriers can start being executed for the rest of the cores. Okay, and this way we are eliminating all those scenarios where, for example, this happens first, then happens second, this happens third, and so on. Cannot happen. So the only option in this case is that either the load happens or the store happens first, right? Either of these two happens, and then either of these two happens. You cannot have a scenario where this happens first and then this happens second. That's not possible, because just the way that you are adding your barriers. Does that make sense? And then another interesting thing is that you can have multiple barriers. Nothing prevents you to saying that barrier number 1, barrier number 2. So typically we think about barriers as this function calls with inputs, and the inputs is the number of the barrier. So what you can have is that, some instructions, barrier number 1, and then this is core number 1. Then maybe you have core number 2 and core number 3. And then maybe you have barrier number 1 here and then some instructions. Maybe you have some instructions here and you have barrier number 2. And maybe you have barrier number 2 here as well. So what this says is core number 3 can just freely execute instructions until it hits this barrier. Once it hits this barrier, it has to wait until all the other cores also reach to the barrier number 2. Core number 1 doesn't have barrier number 2, but core number 2 has. So it means that this next instruction can only happen when we are reaching to this point in core number 2. For core number 2, we have 2 barriers. This first one says that you can start executing things in core number 2 when we are reaching this point in core number 1. Okay. So what it says is that I have to start executing these instructions. Once I reach to this point, then both these and these can run in parallel. When I reach to this point, then I'm free to run this part of the code as well. And this part can happen at any time that I want. Could happen before core 1, could happen after core 1, whatever. But I cannot execute these before we reach to this point in core number 2. Does that make sense? So you can have multiple barriers. You can have many different barriers, many different cores. Question you have? Good? Yeah. So the question is, this is like a stall in processor level? Yeah, it's more of a busy wait. So it's like running an empty for loop forever and ever until it's broken. So it's like a while loop until I tell you not to. That's why the operating system kind of take care of this. It's kind of like, an exception happens, the PC no longer moves forward until the operating system actually tells it to. Say it again. So the question is that now can we do out of order within each core? Yes, I mean, we still can. So that's what I'm saying, that within each core, you still don't know the sequence of the instructions. It can happen any way you want. It's just, we just know that I cannot execute these instructions until this core reaches here. Okay, so the barrier is kind of fence plus some additional synchronization. Okay. So fences added coupled with barriers, it basically can solve all the problems that we care about. It can solve the timing problem and it can solve the reordering problem. So if you use your locks, if you use your barriers and fences correctly, that's all you really need to do. And as I said, this is the programmer's responsibility to actually use the barriers and fences correctly. It's not, hardware not going to add these barriers for you. You have to, when you're writing your parallel program, you have to add these barriers if you need to. Okay, so that's a big thing to remember, and that's why writing parallel programs is really hard, because you need to think about all these timings and you need to add it to your system. Unlike these other things that's hardware just automatically take care for you. All right, and remember, we still have our consistency models and memory models within each core. So if you have sequential consistency, it means that these things cannot be reordered. If you have TSO, it means that the writes should be in order, everything else can be out of order. So you still have your consistency models within this, within each kind of regions of this, within this two barriers and so on and so forth. But what this barriers gives you is the synchronization and to kind of give you the timing between them. Okay, so don't mix this two together. Both of them are still there. All right. So if you remember, I told you that another option of this is what we call mutual exclusiveness. All right. So what we mean by mutual exclusiveness is we can design a system such that we can make sure that one process only has access to the one specific region at any given time. So basically, each region of the memory or each region of the code is only exclusively executed by one code and not the others. So we won't have the race conditions in that sense. So how do we do that? We usually use this, what we call the mutex or locks. What it does is conceptually, if you remember the examples that I gave you, if you have one core and the other core, if we add lock, acquire lock, and release lock for both these cores, what happens is that if you want to create what we call a mutual exclusiveness, we introduce this concept of lock, and this lock is something that is exclusive, which means that only one of the cores can have the lock. Okay, so if both of them trying to acquire, get the lock, only one of them will be successful. We'll talk about how would that work. But for example, if core number one would be successful, then it's guaranteed that until core number one release the lock, core number two cannot get the lock. Okay, so it means that this part has to kind of busy wait until this guy released the lock. Then this one can acquire the lock, start executing this, and release the lock, and then move forward. Okay, so basically what this says is, everybody has an equal chance of getting the lock, but lock can be only assigned to one core only. And if somebody has the lock, everybody else has to wait until the lock is released. Then they can, again, fight for getting the lock. Whoever gets it can continue execution. And remember, what we are doing is that we have acquire release as two different functions for getting and releasing the lock. And anything that happens in between these two is basically the part that is going to be mutually exclusive. All right. Only one core can run this, and everybody else has to wait. Okay. And using this concept of getting and releasing, we're going to have another consistency model, which we call release consistency. Okay. So what the release consistency says, that this is added to our TSO and our sequential consistency, is that if we have this kind of model of getting and releasing, what we can do is saying that, okay, what I'm going to do is that I'm going to say that when I reach to this point, when I'm releasing the lock, it is guaranteed that all the stores and loads that I do within that part is observable and visible to all the other cores. Okay, so I can do whatever I want internally, but when I'm releasing the code, releasing the lock, I've already done everything that I want to do. So all these other cores can now safely start running their things because I already done my things. Okay, so this is what we call usually release consistency, which means that we can assume that when the lock is released, all these other loads and stores are already done on the part that's been executed on this part. So when we are releasing this lock, it is guaranteed that this is done and this is done. So when we are actually reading Y, we're going to guaranteeing that we are reading 100. All right. Or other way around. If you're doing this first, and if you're reading Z, it is guaranteed that we're going to read 200. Okay, so it's not going to be interleaving between them. Again, what happens within each core, it might or may not be reordering. We don't know. Typically, you can do any reordering that you want. But what happens between the cores is that the other core will see everything in order from the other cores. Okay? And that's what we call release consistency. Anything beyond the locks, then there's basically a jungle. Anything can happen. All right. So release consistency says that, oh, I'll see these things when you release. But if there is no lock, then any ordering can happen between any of us. All right. So just be careful about release consistency. Question. Yeah. Z is equal to 200. If core 2 gets a lock, then Z would be equal to 200. If 1 gets a lock, we will talk about how to get the lock, but basically release consistency doesn't tell you which one happens first. It just says whoever gets the lock, once it's released, we will see everything that happens in that. Okay? But still the ordering might be different. So still core 2 might get first or core 1 might get first. The mutual exclusiveness doesn't give you the ordering, but it gives you the exclusiveness. It says that only me or only you, but it could be either me or either you. We don't know. Whoever gets the lock first. The barrier is the one that gives you the ordering. So you basically might need to add, if you really, really want that this happens first, then this happens, then you really, really need a barrier, not a lock. Okay, two separate things. Question? Or you're good? Okay. Any other questions? All right, so now that we understand these things, so let's see how we implement them. So as I said, fence is actually literally an ISA instruction. So you actually need to add hardware support for that instructions. We're not going to go through the details of that because it's a little bit complicated, but fence is actually an instruction. I told you that, barriers are typically, implemented by operating system. We're not going to go through that as well because that's more of like an operating system. You need to change that in the kernel. So probably if you take an operating system, you'll see how these things are being implemented. But let's actually talk a little bit about how we implement locks, okay? We're not going to go through the details as well, but just a basic idea of at least what are the requirements for a lock, okay? So if you think about the actual C code or pseudocode for lock, it looks something like this. So the acquire function is basically just checking the lock. And let's say if lock is equal to 0, it means that nobody has taken it, so the lock is free. And if lock is equal to 1, it means that somebody else has it, okay? So in this case, acquiring the lock means that I'm busy waiting on lock equal to 1. If lock is equal to 1 or not equal to 0, I'm just going to wait and wait and wait and wait until there will be some tiny amount of time that locks become 0. And that's when I'm going to get this lock and then I'm going to do lock equal to 1. So I'm going to, again, change the lock, but that means that now I have it, all right? So I'm not going to leave this acquire code until there will be a moment at which locks becomes 0. So that's why when I'm running this and this together, what will happen is that both of them will be busy waiting here. One of them managed to get the lock first and then going to continue. The other one will not see the lock is equal to 0. So it just keeps sitting there until the locks becomes 1. Locks becomes 0. Okay, so that's what the acquire works. And if you think about the assembly version of this, it will look like something like this. That basically this x1 plus 0, so basically the memory x1, so whatever x1 is pointing to is where the lock is stored. So lock is literally a point in your memory. It's nothing else, right? So what we are saying is that load this, branch not equal to 0, RA, whatever I read here, then keep doing the loop. Keep loading lock, keep reading lock until the point that is equal to 0. And then continue. So what we are doing here is just we are writing 1 to RA and we are storing 1 to lock, right? So basically very similar thing that we are doing here. We're doing busy wait with this branch not equal to 0. And then if it becomes 0, then we write 1 to it and then we move on. All right. So that's the idea of the assembly version. And the idea of the release is very simple. So the release is basically all it does is just write 0 to lock, right? So it would be store 0, like R0 to x1 and 0, right? So store word x0, x1, 0, right? So that's all you need to write for your release, just one single instruction, right? And you don't need to busy wait, because if you acquire the lock, that's when you only call the release. So you are the only one who has it. So there is actually an inherent exclusiveness for your release. You don't need to be worried about acquiring the lock in release. So now let's see that 2 cores trying to acquire the lock at the same time. So both of them will have this code here. This is the acquire code, right? So we are basically at this point in our example. Both of them are at this point. So let's see actually what happens at the clock cycle level. What will happen is, anybody can point out what the problem might be? Yes. So there will be a race condition between these two. Because remember, for acquire still we have any ordering between the cores. So what might happen is that I'll read this instruction first and maybe say that the lock is actually equal to 0. So I'm going to say, oh, great, lock is equal to 0. And I want to start executing this and this. So maybe I execute both of these two, but I still haven't done this. At the same time, this core might also do this before this happening. So if this happens before this, core number 2 also going to read lock equal to 0 and going to think that, oh, I got the lock as well. So then start doing this and then going to reach to this. Maybe then this happens and we write 1. and this happens, we also write 1. But at the end of this, both of them thinks that they have the lock. The reason that both of them thinks that they have the lock is that there couldn't be reordering between them. There is no notion of exclusiveness here. Although the code is kind of makes sense, right? The idea of lock makes sense, but what really happens in hardware is that there's no way of kind of saying that, oh, you only happen first and you only happen next, all right? Unless we add barriers and so on, but let's say we don't want to use barriers. Anybody clear why we have this problem? Okay, so what we should do is that we need to basically have a mechanism that if you're reading from the memory, only one of them reads from the memory and the other ones cannot. In order to do that, we introduced the concept of atomic instructions. So atomic instruction is what it means is that it's the hardware primitives that guarantees that instructions are actually happening in order without any interruptions, which means that if I run this code atomically, I only run this, then this one cannot happen in between, then I can run this. So basically what the atomic will tell you is that you're kind of switching from a multiprocessor domain to a uniprocessor domain. So the hardware will not allow that things to happen in parallel. Only one thing can happen at each time, okay? So when we have atomic, hardware or support for atomic, execution, what it says is that even if we might have multiple cores, even if we might have interruption and all those things, I'm not going to allow it for this period of time. Okay, and if you are adding that to this, all we really need to do is that running these things in atomic fashion. I first run this, maybe then I run this. Whoever gets the log, great. Whoever cannot get the log just has to busy wait for the others. Okay, and this way there will not be a race condition or overlapping between these two, because we are guaranteeing that I'm running this first and then I'm going to run this next. Okay. You might ask, why are we not really running everything in atomic fashion? Because you want to have parallelism. That was the whole point of having multi-cores, but maybe sometimes it would be a good idea to have it. And that would be when you actually implement your atomic instructions in atomic code. Okay, so now that we have this, let's see how we actually do implement the acquire. There are a bunch of different ways of doing this. There is what we call compare and swap, or fetch and add, or test and set. The one that I'm going to describe is test and set, but the other two is also very, very similar. So the idea is that this test and set function, which is kind of like, the implementation of the acquire, is going to get this x, which is basically our lock. And what it's going to do is going to read the lock, okay? And what it's going to do is having this function called swap that is actually atomic, which means that only one swap can happen at one time. And what the swap does is that it reads x and it swap it with 1 and then gets the value and return that value. Okay? So what we do is basically saying that if I read 1, I'm not going to do anything. If I read 0, I'm going to swap it with 1, and then I'm going to return 0. If I read 1, I'm going to return 1. The old value always will be returned. If the old value is 1, it means that the lock is already occupied. I just have to wait. So it's going to test and set. I'm going to test first to see whether the lock is occupied or not. If it's occupied, I'm going to return 1. And if I return 1, it means that I have to wait. But if the lock is equal to 0, that's when I'm going to do the swap. And the swap is atomic, means that only I can do the swap and the other cores cannot. And this way I get 0, which is the old value, which means that lock is available for me, so I can acquire it. And at the same time, I write 1 to the lock so that nobody else can get that lock. Okay? So what really happens here in the timeline is that if I read 1, nothing happens because I'm swapping 1 and 1. So nothing happens. And I'm going to return 1, which means that, oh, the lock is already occupied. So just wait. So busy wait that I was doing before. But if the lock is actually equal to 0, now I'm going to swap 0 with 1, and I'm going to read 0, which means that, oh, the lock is available, it's for me. And I already write 1 to the lock as well, so nobody else can do that. And since this is atomic only, it's guaranteed that only one processor can do that. So the other ones would read 0. Does that make sense? So this is what we call test and set. How do we implement test and set? The test and set needs hardware support, okay? Because we need to do atomic swap. How do we do atomic swap? We do atomic swap with this 2 instruction called load, link, and store conditional, or LL and SC, okay? So this LL means that, remember we had JALR that we read and link something to some address? So this is kind of similar. So what it says is that I'm going to read this address, then start doing something you want with it, and then write to the same address, okay? Similar to the load and store. The only difference is that if in between these 2 instructions, that address has been updated by other cores, I'm going to know this, and I'm not going to store this value to that address, okay? So what it does is that, let's say I'm having this address, and I'm going to load from this address maybe to x2, okay? And then I'm going to run a bunch of instructions, and I'm going to write the value to this address, okay? So there are some instructions happening in between. And not only for this core, there will be some instructions and things that might be happening in all these other cores, okay? There might be a scenario that some other cores decided to write to this line. What this store conditional says is, once I reach to the store part, I'm going to tell you that the value that you read was the clean value, or was it the now it's dirty? If it's dirty, then I'm not gonna store things to that line, because someone else already did that. All right. So it's not a regular store, regular load. The difference is I'm loading similar as before. I'm just going to that address, bring that data, but I'm gonna also remember what I read. And when I want to write, when I want to store, I'm going to check whether this is still the same value as before or not. If somebody else has updated this, then I cannot write to it because somebody else already did that, okay? And this line is actually your lock, okay? So basically what this says is that if you're reading your lock, and if somebody else during that process of reading and changing things and writing back to the lock again, change the lock, then what you read was invalid. You need to just discard it. Okay, so the load, link, and store conditional is actually what's been implemented on RISC-V, again, at the ISL level, so there is hardware support for it. And all it does is basically tell you that if you read something that's been updated, you cannot write to it. You have to just discard it. Okay, so the store doesn't always happen. It's not guaranteed that it's always happening. Does that make sense? All right. So with this LR and SC, or LL should be actually. What we basically do is that we are telling that we know what we have loaded, and if somebody else changes that, then we're going to fail. Okay, and the implementation of this is actually quite interesting. You can actually use your coherence protocols, like for example for MESI. All you need to do is saying that whether you're exclusive or not. If you are exclusive, then it's guaranteed that you will be the only one who's writing to that. If there is someone else that tries to write to that address, if someone else goes to E or M during this process, that's all you need to know, right? That means that some other cores try to access that address, which is the lock, and I need to just invalidate myself. Okay, so it's very simple to actually implement this in hardware. All you need to do is actually combine this with the coherency states. Okay. So to recap, what we said is one of the ways to make sure that things are exclusive is using locks, okay? And in order to implement locks, you need to implement a function called acquire, and you need a function called release. Okay. Do acquire one, it basically says that I need to read some part of the memory which we call lock. And we need to keep reading that until the lock becomes 0. But the problem is that all these other cores are also doing the same thing. So we need to have a notion of exclusiveness to this. All right. So if you just run it simply same as before, that's not going to happen. So what we are proposing is the concept of atomic swap or atomic instruction. And we add that to what we call a test and set, which basically all it does is testing the value. If it's not set, we set it atomically. And we're going to get the lock based on that and make a decision based on it. So I'm going to busy wait until the lock becomes 0. As soon as it gets 0, I'm going to write 1 to it. And only one core can do that, and the other cores cannot do that. And that way, I'm going to acquire the lock. And when I want to release it, I'll just basically write 0 to it. How do I implement that? I'm going to use this concept called load, link, and store conditional, which basically all it does is just monitoring that line and see if the other cores are trying to write to that line. I'm going to just discard my writes. That's no longer atomic. There is an interruption, so I need to discard that. Okay? As I said, there are other ways of, instead of doing test and set, we do things like fetch and add, or replace, and so on and so forth. But test and set is just, basically the idea is something like that. Any questions? So, and as I said, locks are actually the ones that we typically combine with release consistency. And we're going to get release consistency basically saying that, okay, at the end of my lock, release of my lock, if I make all the reads and writes transparent and available, observable to everybody else, then I can have a memory model that we call release consistency model. Question? You. So the question is, what determines how long the lock is? The programmer. The programmer literally put lock in their code. Okay, so they actually write a C code that has this line of acquire lock. So there's actually an API, a function call that you put in your code to acquire the lock. All right. So that's why I'm saying it's on the programmer to do that. And then they have to release it. If you forgot to release it, then your code won't work. There will be in a deadlock situation, basically, because you never release it and everybody else has to wait. What? Say it again. The lock, the question is, the lock is done by the OS, the implementation of it. So the implementation of the lock is, yes, a combination. So it's similar to, let's say, printf in some sense. It's standard library in some sense. So when you call it, the operating system needs what to do. But what the operating system does really is using this hardware support that we add with the atomic instruction and store load conditional, load link and store conditional. So operating system alone cannot do the locking for us. It needs hardware support, and that hardware support is atomic instructions that is implemented by load link and store conditional. Does that make sense? But basically, yes, what is happening is if you really go into the acquire code, but by the way, it's available online, for example, for Unix systems, you will see that's how it's being implemented. And you will see that there is some form of, something like this that we kind of explain here, basically. Right? So something like this is actually happening. Any questions? So similar to many other things that we discuss in this course, there are optimizations for this. So the basic concept is, yeah, there will be busy wait, and then we're going to test that. But what you can do is improving this in order to do less busy waits and so on and so forth. I'm not going to go through the details, but there is what we call a test and set. There's things as like a test, fetch, and add, and so on and so forth. What they do is basically saying that your busy wait could be a little bit more efficient. So instead of like keep reading the log and keep writing to the log, doing lots of unnecessary swaps, maybe first read the log, and if it's not there, don't write anything to it. So first test, then do test and set. Because in test and set, you're swapping 1 with x anyway. And if your x is equal to 1, you're writing 1 to 1. Right? So you're basically doing a very, very wasteful thing, but the hardware doesn't know that. The hardware just sees this store words. So what we are proposing is that do the test first. If the log is not even equal to 0, then just don't do the swap. Do the test and then do the test and set. Okay? So again, I'm not going to show you the code, but you probably get the idea that you basically do the while, but we don't do the swap. We just do read, the normal read from the log. Still, everybody has to read the log, but you just don't need to swap it with 1. Okay? If it's 0, then do the swap. Just add a little bit more delay to acquiring the log, but at least it saves a lot of stores. Because on normal case, there will be only one core that has the log, and everybody else is kind of like busy waiting. So there will be lots and lots of stores, unnecessary stores happening here, because remember, we are doing swap 1 and x, right? And this, if x is already 1, you are basically swapping 1 and 1. Completely unnecessary thing to do. Okay? So the idea is read the log first. So maybe just load x. If x is equal to 0, then do the swap. Remember, still this has to be atomic, otherwise there will be overlapping, but the load part doesn't matter. There might be 2 of them worst case scenario, but there won't be a correctness issue. Okay? There's also the question of, oh, what if there are multiple different cores and all fighting for 1 log? What we can do in order to fix that, we usually use queues, okay? So if core number 1 wants the log, core number 2 wants the log, and core number 3 wants the log, what they can do is that they put the request into some form of a queue, and then we service the first item in the queue. And instead of like making it open to the world and say, okay, whoever wins it gets it, we're gonna say that, oh, core number 2 wanted before you, so let me actually serve core number 2, and so on and so forth. This is actually adding some notion of fairness to your system. All right. And then similar to barriers, you can have multiple locks. Okay. So you don't need to have only 1 lock. So you might have some portion of code and some other portion of code that needs to be mutually exclusive, but not necessarily from each other. So you can have 1 lock and another lock and another lock and another lock and so on and so forth. You can have many different locks for different parts of your code, and you can have, you might acquire 1 lock but not the other lock, and so on and so forth. I'm not going to go through the details of this, but there's a whole bunch of, how do we avoid, deadlocks, how do we do multiple locks, and so on and so forth. If you're ever doing some form of parallel programming class, you will see all these things, because there will be scenarios that you need these kind of things. Okay. All right. So that's it for consistency. There are a range of possibilities for consistencies. There are different memory models, and there are a whole bunch of different synchronizations. You have to kind of understand all these and kind of be able to combine all of them. Sometimes you need fences, sometimes you need locks, sometimes you need to know your memory model, and sometimes you need, add barriers and locks and fences all together. All right? So good luck. And this is basically the end of our lectures in some sense. Thanksgiving, we don't have class, and happy Thanksgiving, by the way. And next week, I'm just going to review the things that I say, and I'm going to go through some of the advanced topics, all right? That's not going to be part of your quiz. So your quiz would be whatever we say today.